Hey there, fellow explorers of the mathematical cosmos. Today, we're embarking on a thrilling expedition to the realm of calculus, where we'll be grappling with a concept that's both mind-boggling and awe-inspiring: limits at infinity. Imagine yourself on a spaceship, venturing further and further into the vast expanse of space. As you journey into the great unknown, you might wonder what happens to the fabric of space-time as we approach infinity. Do the laws of physics as we know them still hold true? In the world of calculus, limits at infinity allow us to explore the behavior of functions as their inputs, or the values we plug into them, grow infinitely large or infinitely small. They provide us with a powerful tool to understand how functions behave at the edges of our mathematical maps. Just like intrepid astronauts pushing the boundaries of human exploration, we'll be pushing the boundaries of our mathematical understanding, so fasten your seatbelts and get ready for an adventure into the infinite.
Picture yourself sailing across a vast ocean, the sun dipping below the horizon. The farther you sail, the closer the horizon seems to get, yet it never quite touches the sky. In functions, horizontal asymptotes are like that distant horizon. They are lines that the graph approaches but never reaches. Imagine f of x equals 1 over x. As x gets larger, f of x gets closer to 0 but never reaches it. This line is the horizontal asymptote.
In the world of limits at infinity, we encounter functions that exhibit an insatiable thirst for growth, their values skyrocketing towards infinity as their inputs venture further and further along the number line. Consider the function f of x equals x squared. As x grows larger and larger, the value of f of x increases at an accelerating pace, shooting upwards towards infinity. We say that the limit of f of x as x approaches infinity is infinity. Infinite limits can be visualized as functions whose graphs soar upwards or plunge downwards without bound, like rockets launching into the cosmos or meteorites hurtling towards Earth. They represent functions that exhibit unbounded growth or decline. Understanding infinite limits is crucial for analyzing the behavior of functions that model real-world phenomena, such as population growth, radioactive decay, or the spread of diseases.
Imagine yourself as a zoologist studying a newly discovered species. You'd want to understand how it interacts with its environment. Similarly, in calculus, we study the behavior of functions at their extremities, as input values approach positive or negative infinity. This is where end behavior comes into play. It shows us long-term trends and the shape of the graph at its edges. By analyzing leading terms, we determine end behavior. For example, x cubed grows infinitely large as x approaches infinity. End behavior helps us predict function trends.
Section 5. Unraveling the mysteries of rational functions. Rational functions, those formed by the quotient of two polynomials, can be a bit like puzzles, their behavior often shrouded in mystery. But fear not, intrepid explorers of calculus for limits at infinity provide us with the tools we need to unravel their secrets. When dealing with rational functions, the key to understanding their behavior at infinity lies in comparing the degrees of the numerator and denominator. If the degree of the numerator is less than the degree of the denominator, the function will approach 0 as x approaches infinity. Conversely, if the degree of the numerator is greater than the degree of the denominator, the function will grow without bound as x approaches infinity. And if the degrees of the numerator and denominator are equal, the function will approach a horizontal asymptote. By mastering the art of analyzing rational functions at infinity, we gain a deeper understanding of their behavior and can unlock their hidden patterns and relationships.
Section 6. Exponential functions, soaring to infinity and beyond. Exponential functions model phenomena like population growth and compound interest. Their behavior at infinity is intriguing, showing explosive growth or rapid decay. The function f till x equals 2 to the power of x demonstrates exponential growth. Functions with a base between 0 and 1, like f x equals 1/2 to the power of x, decay rapidly.
Section 7. Trigonometric functions dancing with infinity. Trigonometric functions, those elegant dancers of the mathematical world, exhibit a unique behavior at infinity that sets them apart from other function families. Unlike polynomial or exponential functions, trigonometric functions don't approach a specific value or infinity as their input values grow without bound. Instead, they oscillate, their graphs resembling waves that rise and fall in a rhythmic pattern that continues infinitely. This oscillatory behavior reflects the cyclical nature of trigonometric functions, which are defined based on angles and the unit circle. For example, the sine function, denoted as sin x, oscillates between -1 and 1 as x approaches infinity. Similarly, the cosine function, denoted as cos x, exhibits the same oscillatory behavior. Understanding the behavior of trigonometric functions at infinity is crucial for analyzing periodic phenomena, such as sound waves, light waves, and alternating currents. Their rhythmic dance across the infinite expanse of the number line provides a glimpse into the elegance and order that underlie many natural processes.
Section 8. Limits at Infinity, a Symphony of Concepts. As we've journeyed through the world of limits at infinity, we've encountered a symphony of concepts, each playing a crucial role in understanding the behavior of functions as their input values approach positive or negative infinity. We've explored horizontal asymptotes, those guiding lines that functions approach but never quite reach. We've delved into infinite limits, where functions exhibit unbounded growth or decline, their graphs soaring towards the heavens or plunging into the depths. We've tamed the wild world of functions with end behavior, analyzing their long-term trends and predicting their behavior at the edges of our mathematical maps. And we've unraveled the mysteries of rational, exponential, and trigonometric functions, uncovering their unique behaviors at infinity. Together, these concepts form a powerful toolkit for analyzing functions and understanding their behavior in the realm of the infinite.
Section 9. Applications of limits at infinity, from physics to finance. Calculus models real-world problems. Limits at infinity apply in physics, engineering, economics, and finance. In physics, they model object motion and planetary orbits. In economics, they analyze market trends and equilibrium. In finance, they model investment growth and risk.
Section 10. Common misconceptions and pitfalls. As with any powerful tool, limits at infinity come with their own set of common misconceptions and pitfalls that can trip up even the most seasoned calculus enthusiast. One common misconception is that a function must approach a specific value as x approaches infinity. While this is true for some functions, such as those with horizontal asymptotes, other functions, such as trigonometric functions, exhibit oscillatory behavior, never settling on a single value. Another pitfall is assuming that a function can't cross its horizontal asymptote. While the definition of a horizontal asymptote states that the function approaches the asymptote as x approaches infinity, it doesn't preclude the function from intersecting the asymptote at one or more points. By being aware of these common misconceptions and pitfalls, we can avoid making costly mistakes and ensure that we're using limits at infinity correctly to analyze and understand the behavior of functions.
Section 11. Mastering limits at infinity tips and tricks. Mastering limits at infinity, like any skill worth acquiring, requires practice, patience, and a dash of strategic thinking. Here are a few tips and tricks to help you navigate the world of limits at infinity with confidence. First, start with the basics. Before diving into complex functions, make sure you have a solid understanding of the fundamental concepts of limits, such as approaching from the left and right, and the limit laws. Second, visualize with graphs. Graphing functions can provide invaluable insights into their behavior at infinity. Use graphing calculators or online tools to visualize functions and their horizontal asymptotes. Third, break it down. When dealing with complex functions, try to break them down into simpler components using algebraic techniques. This will make it easier to analyze the behavior of each component at infinity. Finally, practice, practice, practice. The more you practice evaluating limits at infinity, the more comfortable you'll become with the concepts and techniques involved. Seek out practice problems in your textbook or online resources.
Section 12. Conclusion. Embracing the power of limits at infinity. As we conclude our journey into the realm of limits at infinity, we've gained a newfound appreciation for the power of this concept to unlock the secrets of functions and their behavior at the edges of our mathematical maps. We've explored horizontal asymptotes, infinite limits, end behavior, and the unique behaviors of rational, exponential, and trigonometric functions at infinity. We've also discussed applications of limits at infinity in various fields and highlighted common misconceptions and pitfalls to avoid. Armed with this knowledge, we're now equipped to tackle more complex calculus concepts and apply our understanding to real-world problems. So embrace the power of limits at infinity and continue your exploration of the fascinating world of calculus.